Thank you. Thank you, Ala, for the introduction. So I want to thank the organizers for the invitation. So in the first part of my talk, I will introduce the problem and discuss some relevant literature, introduce our research program, and give some preliminaries which will be necessary for the second part. Okay. Yeah, so the study of pseudo-Riemannian metrics on smooth manifolds is an important topic in differential geometry and with application in cosmology and general relativity. And the fundamental issue is that pseudo-Riemannian metrics often fail to be geodesically complete, even in the compact case. And this is given by the example of Clifton-Paul torus. I will give it in a minute. Okay, so we consider M. Going to change this to be R2 except the origin, and I define Lorentzian metric given by 2dx dy x squared plus y squared. And for this setting, you note that any homothéty is an isometry, in particular this homothéty, which multiply by 2, okay? Because you get lambda square in each part, and then you simplify. Okay. I defined the group generated by lambda. This is isomorphic to Z. It's given by the iterates of lambda, and we quotient M by gamma. Okay. Gamma acts properly discontinuously on M, so we get a nice quotient. In fact, it's topologically a torus. So I will try to draw a fundamental domain. Okay, so for example, the circle of radius 1 and the circle of radius 2. Okay, and this will be a fundamental domain of this quotient. And identifying these two circles, we'll get the torus. Okay. So it's the quotient is compact Lorentz manifold, but it has an incomplete geodesic given by this. In fact, it's nil geodesic. It's incomplete at 1. Okay, so for these reasons, we would like to investigate geodesic completeness for a particular class of pseudo-Riemannian manifolds. This class is Lie groups with left-invariant pseudo-Riemannian metrics. Okay, so first of all, I will define what is a Lie group. So a Lie group is a differentiable manifold for which the group multiplication and the inverse operation are smooth maps. And the usual examples are these are Rn with with the addition of vectors. S1 is a Lie group, S3, and they are the only spheres that are Lie groups. These are matrix groups, SLN and UN. And SL2R is not a matrix Lie group. The universal cover of SL2R is not a matrix Lie group, but it's still a Lie group. Okay. We define Lie algebra to be a vector space which has an additional operation. It's called the Lie bracket. It's alternating bilinear map, which satisfies the Jacobi identity. Okay, and these two objects, they have some correspondence between them, Lie groups and Lie algebras. So first, the tangent space at the identity of a Lie group is a Lie algebra. with the brackets given by the commutator of vector fields. And for Lie algebra, we can associate uniquely up to isomorphism a simply connected Lie group for which the Lie algebra is G. Okay. So I will give some examples of Lie algebra. So if you take the Lie algebra associated to the Lie algebra associated to GLN, it will be Mn, the algebra of matrices. If you take the Lie algebra associated to SLN, it will be traceless n by n matrices. If you take the Lie algebra of SUN, it will give you traceless n by n complex matrices satisfying the transconjugate is minus the matrix. So these are some linear examples. Okay, and for all these matrix examples, the bracket is the usual commutator. Okay, and we denote the bracket of X to be at X. Okay. I defined the Lie algebra. It's the algebra of brackets of vectors X, Y, and G. It is a subalgebra. And the center is given by vectors which commutes with all Y in G. And a Lie algebra is said to be solvable if this following derived series ends to a zero subalgebra. Okay. And if you take the central series, it goes to, so we see that it is nilpotent. So another important definition is unimodular. So if a Lie algebra is said to be unimodular if the trace of add X is zero for all X in G. This add X is the bracket of X. Okay. And the connected Lie group is said to be unimodular if its associated Lie algebra is unimodular. So now we will go through the classification of Lie algebra in low dimension, and I will put in red the unimodular ones, okay? So in dimension 1, we have only R up to isomorphism. In dimension 2, it's either abelian or the affine algebra, and the abelian one is unimodular, and the affine algebra is the Lie algebra associated to the affine group of R. Okay. So this is for dimension 1 and 2. For dimension 3, we have no longer finitely many of them. We have infinitely many Lie algebras. So if the derived algebra is 0, this means that it's abelian, so it's R3, and it's unimodular. If the derived algebra has dimension 1 and the derived is included in the center, so this will give the Lie algebra of the Heisenberg group. If not, I mean, if the dimension is still 1, but the derived algebra is not included in the center, this gives you the algebra affine plus R, so which is direct sum of the affine R we already defined in dimension 2 with R, and it's not unimodular. And now if the dimension of the derived algebra is 2, we get 3 subcases. So the first case is if we have some Z in G, but not in the derived, which is diagonalizable over R, then there exists some lambda such that G is isomorphic to this Lie algebra H lambda given by these non-zero brackets relations. So basically, E2 and E3 commutes, and the bracket of E1 with E2 is E2, and E1 with E3 is lambda E3. Okay, so can say that the add of, if we write the matrix of the add of E1, it will be something like this. Okay, in the basis E1, E2. Okay, and in the case where lambda equals -1, you note that this the matrix will be traceless, and all the other adds are traceless. We'll get the Lie algebra of rigid motions of Minkowski 2 space. Okay. And in fact, this algebra is unimodular. Okay, so if not, I mean, if it is not diagonalizable, if it is trigonalizable over R, then it must be isomorphic to this Lie algebra. We call this Lie algebra the pseudo-homothetic Lie algebra. Okay, and it's given by this bracket relation. I will come back to this algebra later. So you can say somehow this this first class is hyperbolic algebras, and this one is parabolic. So you can guess the last one is elliptic algebra. So if it's not diagonalizable in R over R, so it must be it must have two complex conjugate eigenvalues, and in which case we can find some theta for which our Lie algebra G is isomorphic to A theta given this way by this non-zero commutation relation. So basically, E2 commutes with E3, and the add of E1 is given as follows. For some theta between 0 and pi over pi. And in the case where theta is pi over 2, we get the Lie algebra of the Euclid group. So it's for pi over 2, we get this matrix as the add of E1. As you can notice, it's traceless, and this is the Lie algebra of the group of rigid motions of the Euclidean 2D space. Okay, which is SO2. If you want the simply connected one, it's R semi-direct with R2. Okay, via the exponential of this matrix. Okay. And in the case where the derived is of dimension 3, this is the case of simple algebras. They are either in dimension 3 SU2 or SL2R. Now we get into the left-invariant matrix. So we take a Lie group, connected Lie group with a pseudo-Riemannian metric. Then this metric is said to be left-invariant if the left multiplication is an isometry of this pseudo-Riemannian manifold. Okay? And there is a one-to-one correspondence between left-invariant matrix on G and symmetric non-degenerate bilinear forms on its associated Lie algebra. So if you have a left invariant metric, and you take it as the identity element, it will give you a symmetric non-degenerate bilinear form on G. And the opposite side, you translate this symmetric non-degenerate bilinear form over the group, and you get the left invariant metric. Okay. And this is very important thing, because it allows us to study left invariant metrics at the Lie algebra level, and without loss of generality. Okay. So afterward, we will do all the study at the Lie algebra level. Okay. So now I will go through some literature on this topic. So first, we have the result of Marsden, so which shows that homogeneous compact pseudo-Riemannian manifolds are geodesically complete. Then we have Ghediri, who shows that two-step nilpotent Lie groups have all their pseudo-Riemannian left invariant matrix complete. And then Ghediri again shows that the Euclid group has all its left invariant Lorentzian matrix complete. Okay. And then in 2008, we have Bromberg and Medina who made a characterization for completeness in dimension 3, in the unimodular dimension 3. So as you saw, we have 6 unimodular Lie groups. So we have SU2, SL2R, Euclid group. We have the group of rigid motion of Minkowski to space. And we have Heisenberg and R3. Okay. For these 6 cases, Bromberg and Medina was able to characterize the completeness by the non-existence of something called the idempotence. So I will come back to this later. Okay. And the most progress on this topic of geodesic completeness we know is due to the work of Shafi'i, Ferreira, Sanchez, and Zeghib. So what they did, they show that they defined the notion of linear geometric growth, which is given by this bound, where this is a norm on the Lie algebra, and this is a distance on the group, and the left invariant metric on the Lie group. And they show that if a Lie group satisfies this, we say that it is of linear geometric growth. They show that this list of groups have all their semi-Riemannian metrics complete. Okay, this is recent work, and this is the most progress we know in the literature. Okay, so for us, our research program is we had this remaining Lie algebras in dimension 3. They come in 1-parameter families and discrete classes. So for instance, we have here 1-parameter family of Lie algebras in the elliptic case. Okay. What is it? Yeah. And we have this parabolic one in this parabolic class, which we call the pseudo-homothetic Lie algebra. And we have this 1-parameter family of hyperbolic Lie algebras. And we have a affine algebra plus R. So these algebras, for these algebras, the geodesic completeness of left invariant metrics remain uninvestigated. Okay. And so the first objective of our research program is to make a complete classification of left invariant metrics in terms of completeness for these non-unimodular Lie groups. And the second thing is to determine three-dimensional Sumerian Lie groups with higher dimensional isometry groups. So usually the translations are isometries, and sometimes we have some extra isometries. So in general, it's the dimension of the isometry group is 3 generically, but we aim to determine the cases where we have extra symmetries, where we have higher dimensional isometry group. Okay. So now I will go through some preliminaries that we will need them for the second part. For this talk, I will go through the completeness problem, which is this first problem. Okay. So for that, I need some preliminaries. So if we take a pseudo-Riemannian manifold, so in local coordinates, it's written this way, with the Gij makes a symmetric non-degenerate matrix of a given signature. The corresponding Christoffel symbols are given this way, using the Einstein dummy notation of indexes. So when you have a repeated index, you sum all over this index. And a curve defined on M is geodesic if it satisfies this equation. Okay? This is in general. Now, for Lie groups with left-invariant matrix, we can do better. Okay? So what we do what's called the Euler-Arnold formalism. Okay, so we have our Lie group G, okay, and we have some curve gamma on G. We have the identity element, and the Lie algebra is the tangent space here. So what we do, at each time t, we translate the gamma dot of t into the identity element. Okay, and we do it again and again. So maybe here, here, here. And this will make a curve on the Lie algebra level, and we will call this curve x. Okay. So x of t is the pullback by gamma of t of gamma dot of t. Okay. So we translate the velocity curve into the Lie algebra. So this will make this curve x. Okay. And then the Euler-Arnold theorem states that using this curve, we can determine whether a gamma is a geodesic or not of G using this equation. So if the corresponding x satisfies this equation, we say that gamma is a geodesic. So what is this equation? So for this notation of dagger, so this is the formal adjoint. So if the metric at the identity is denoted by Q, so the formal adjoint in general of some A is B, which satisfies this for every X and Y in G. Okay, so here we say that B is the adjoint, the formal adjoint of A. Okay, and here the equation is x dot equals at x of t dagger x of t. So we take the add x of t, which is the bracket with x of t. We take this linear map, we make its adjoint with respect to the metric, and we act on x of t. Okay, this equation is homogeneous and quadratic. We can see that if you replace by lambda x, so we'll get lambda from here and lambda from here. So it will lambda square goes out. So it's a quadratic homogeneous equation. Okay, so we made a corresponding quadratic homogeneous equation to our problem, which seem a bit complicated in general, but in the case of left-invariant matrix, the study, the analysis are simpler. Okay. Yeah. So yeah. Now I come back to this idempotent. So for if F is a homogeneous quadratic vector field, an idempotent is a solution of this equation, a non-trivial solution of this equation. So it's some x0 such that f of x0 equals x0. Okay, and the existence of a vector like this implies incompleteness. So okay, I write the equation of this. But what Bromberg and Medina did, they did that if they make this sufficient condition necessary. So if you take a unimodular Lie group with a left-invariant metric, and you write the Euler-Arnold vector field, let's us denote it by F. So x dot equals Fx. So what Bromberg and Medina did, they said that if GM is incomplete, if and only if there exists some x0 and idempotent of this geodesic vector. Okay, and this is in fact not true. It's not true in the non-unimodular case. We'll see many examples later. Yeah. So why for instance the existence of an idempotent imply the incompleteness? So in fact, so if we have such an idempotent, let's say x0 in G. So remember that the geodesic equation x dot equals add x of t is defined on the Lie algebra G. So if we have such an idempotent, we can associate the following incomplete curve. On G such that gamma dot is alpha dot is alpha square. Okay, and this is the typical incomplete equation. So it has solution of this form. And it's incomplete at time 1 over x. I mean, this is in dimension 1, okay? This x0 is not this one, so maybe I will change the notation. Yeah. So this is the typical example of an incomplete equation in dimension 1. And an idempotent gives a rise to this kind of equation. So it implies the incompleteness in general. It's a useful tool in general, but it's not always true. So what Bromberg and Medina did is in fact sharp. So in the sense that if they said that a Lie group, a unimodular Lie group for unimodular Lie groups we have the equivalence between non-existence of idempotence and completeness. So in fact, this is, we have counterexample in dimension 3 non-unimodular, and we have a counterexample for unimodular Lie groups of higher dimension. So this is only true for unimodular Lie groups of dimension 3, what Bromberg and Medina did. Okay. So I think, yeah, I think that's all for the preliminaries.